14.3 talks about partial derivatives, something new we're going to be playing with. The partial derivative of a function z equal f of xy with respect to x at a point xy, x sub 0, y sub 0, would be written in so many different forms depending on which class you're taking. The most three used are really those, and this is the star. That's normally what we write. That is the limit as h approaches 0. You notice x is varying, but y remains constant, provided the limit exists. And if I take the partial of z with respect to y, so this is with respect to x, this is with respect to y at the point x sub 0, y sub 0. Well, the same thing, this is what we're going to be using mainly. Here you notice they hold x constant and they vary y. And I'm going to start the first example by using the actual definition. It says, use the definition of the partial derivative to find f sub x. F sub x is the limit as h approaches 0 of f of x plus h y minus f of x y all over h. That is the limit as h approaches 0. F of x plus h is x plus h squared y minus x plus h y cubed, minus f of xy is x squared y minus xy cubed all over h. That would be the limit as h approaches 0, x squared plus 2xh plus h squared times y minus x y cubed minus h y cubed minus x squared y plus x y cubed all over h. That would be the limit as h approaches 0. And if I distribute the y in, that is x squared y plus 2xyh plus yh squared. And I'm going to copy the rest. Now I notice those two drop off. No need to copy them. All over h. Let me give that a bit more room. And let me make that look a bit nicer. That would be the limit as h approaches 0. And let's see, those two cancel out. I notice all the remaining three terms containing h. I factor that out. 2xy plus yh minus y cubed all over h. The h's cancel out. And how do you find the limit? Once you cancel the 0 over 0, you replace h by 0. And that would be 2xy plus y times 0 minus y squared. And that would be 2xy minus y squared. This is if we're using the definition. If we're not using the definition, this is what it means. Partial derivative. The notation f sub x is like a 2, partial with respect to x of f. That is, go to f, take a derivative of x, not like implicit differentiation. This is much easier. You treat anything that's not an x as a constant. If this y was a constant, let's say that was a 5, wouldn't you bring the power down, subtract 1 from the power, and drag that with you? And if I'm looking at negative x times 5 cubed, and I say take a derivative, isn't that just 5 cubed? So this part is very simple. If you take the partial with respect to x, treat anything that's not an x like a constant. So this differentiation is simple, but when we go back and undo it later on, that's going to require a bit more work. Now, if f of xy, I want to show you what it does. If f of xy is the square root of 9 minus x squared minus y squared, we know what that is because that says z equal a square root. I'm going to erase this. I'm just showing you what it is. z squared equal 9 minus x squared minus y squared, z squared plus x squared plus y squared equal 9. We know that's a sphere. Again, this is just, and since z equal the positive, it's the upper half of a sphere. And I already sketched the graph on GeoAlgebra. As you know, we are a big fan. And I want to demonstrate what this means really. There. So if I want to take the partial with respect to x, wouldn't you say that's 1 over twice the square root of 9 minus x squared minus y squared? No need to write so small. F sub x is derivative of a radical is 1 over twice the radical. That's hopefully common sense. We derive that over and over, times the derivative of the inside by the chain rule. Well, since I'm taking a partial derivative, everything is a constant except x times negative 2x. The 2's cancel out. Evaluated at 2, 0, f sub x would be a negative 2 over, if I put a 2 in for x and a 0 for y, that's the square root of 9 minus 4, 5. Okay. Now, I want to take the derivative with respect to y. F sub y is 1 over twice the radical as well. As far as y is concerned, that's the only variable. These are constants, so the derivative of those will be 0 times negative 2y, evaluated at 2, 0. If y equals 0, I'm going to get f sub y to equal 0 over radical 5, which is simply 0. Now, what does that mean? If I take the point 1 at x equal 2, y equals 0, if I plug 2 and 0, that will be the square root of 5. That's a point on the sphere. It's right there. It's that point I'm pointing to. If I look for f sub x, I'm looking only in the x direction. There's the x. In the x direction, if I am at that point, the slope of that line is negative 2 over radical 5. If you are walking on this sphere, if you got to that point right there, that we pointed to, at that point, the velocity will be that much. If I look at this in the direction of y, y is right there. In the direction of y, so going left and right, you really have a slope of 0. You're not feeling anything. The only force down is really in the direction of x in this case. That's what that means. Just wanted to illustrate what that means. So f sub x, you hold everything else constant, and you just assume x is the derivative. And f sub y, you hold everything constant, you just treat y as a variable, everything else is a constant. So if I'm looking at a derivative of work, where you have worker hours, machinery, rent, utilities, if I take f sub w, I'm going to figure out the rate of change of my cost function in terms of workers only, or utilities only. It has a lot of applications. We're going to be playing with that toward the end of chapter 5 when we do those work problems. For now, we're going to really get this under control, and let's see how this works. Meaning we want to practice this so that we could become, so it can become really easy to use. So, find f sub x, f sub y. Find the first partial derivatives. F sub x, I see a power function. Bring the power down, subtract 1 from the power, that's the traditional derivative, times the derivative of this with respect to x. Since it's a partial derivative, I'm treating everything as a constant except for x. Derivative of 3x is a 3. There. it is done. So differentiation using partial is very simple. What about f sub y? Well, that is still you're going to bring the power down, subtract 1 from the power, times the derivative of this with respect to y is only a negative 5. So I treat everything as a constant except for I'm taking the derivative with respect to. Part B, if I take a derivative with respect to x, x is the only variable. Derivative of x squared is 2x. If this was x times 5, and I said take a derivative of 5x, wouldn't you say it's only 5? So that part you want to get used to. And the derivative of a y function is really 0. You don't have to write that down. That would be my partial of f with respect to x. If I take the partial with respect to y, that's a constant, that's a 0. Here, I'm switching the order. Since I'm taking the derivative with respect to y, I'm thinking x is a constant, assume that's 5y. Derivative of that wouldn't just be the 5, and a derivative of just a y function that's traditional, bring the power down, subtract 1 from the power. Not that hard, really, very easy to use, very useful for what we need. Here, if I want to take f sub x, you're treating this, as far as x is concerned, like saying 5 to the x. That's an exponential function. What do you do with an exponential function? You get the exponential function times natural log of the base times the derivative of the power, which is 1. Assuming y is positive, of course, and satisfy all the conditions. So I'm waving my hand over that. What about f sub y? If I'm looking at this as f sub y, that looks like y to the 5th power. How do you take a derivative of that? You bring the power down, subtract 1 from the power. So partial derivative varies from a regular derivative. It's much simpler and it has its own applications. And let's make sure that we're getting this down. So I'm tackling on all the different types of problems we might come across in this section and the coming sections. What would be f sub x? As far as x is concerned, that's a constant. You ignore it. What's the derivative of cosine? Negative sine of x minus 3y times the derivative of the argument, which is a 1. Done deal. What is f sub y? That's the product rule. Derivative of the first times the second plus the first derivative of a cosine is negative the sine times the derivative of the argument, and the derivative of the argument would be, with respect to y, would be a negative 3. And that would be my answer. So it takes a bit of time to get used to, but students tend to really get this quickly. How about here? F sub x. Derivative of a log is 1 over the argument, especially a natural log, times the derivative of the argument with respect to x, that's a. Done. Derivative of f with respect to y, derivative of a natural log is 1 over the argument, times the derivative of the argument with respect to y, that's b. So hopefully we're getting the hang of this. And here, when I want to take f sub x equal, and in the beginning it helps to put numbers, treat this like e to the x over 5. Because as far as x is concerned, y is a constant. So that would be derivative of an exponential is the exponential times, what's the derivative of x over 5? Isn't that 1/5? But what's taking the place of 5? A y. That would be it. And if I take f sub y, the partial with respect to y, I'm switching the order. Now I'm thinking of e to the 5 over y. Well, derivative of an exponential is the exponential, that's the good news, times. What's the derivative of 5 over y? Isn't that negative 5 over y squared? But what's taking the place of 5? Really an x. It takes a bit of time, but again, students tend to really pick this up very fast. And if they ever come across implicit, That is, what if they don't have z on one side, everything else on the other side? That could happen. So a bit confusing. You're looking for a derivative of z with respect to x. So here, any x that you see, you take a derivative as you do. But if you see a z, it's going to be z sub x. So here, derivative of z is z sub x equal. Here, the product rule. Derivative of the first is a 1 times the second, plus the first derivative of z squared. Bring the power down, subtract 1 from the power, times z sub x, plus derivative of this function with respect to x. As far as x is concerned, this is a constant. So if I'm taking the derivative of 5x, that would be 5. That's y squared. Plus, and here, this is a constant, so you ignore. Take a derivative of z, that's z sub x. And here you really need to get all the z sub x's on one side. So that will be z sub x minus 2x z sub x minus y z sub x equals z squared plus y squared. If you factor z sub x out of all of those, if you take out the z sub x and divide, you'll have a 1 minus 2xz minus y. So the answers don't look pretty, but you know that's how implicit always is. And if I take a derivative of z with respect to y, then y is the variable and z is like saying y equals, so derivative of this will be z sub y, and here this is a constant, you ignore, bring the power down, subtract 1 from the power times z sub y, plus derivative of this with respect to y, bring the power down, subtract 1 from the power, and derivative here requires the product rule. Derivative of y is a 1 times z plus y times z sub y. The same deal, get all the z sub y's on one side. So I'm going to get z sub y minus 2x z sub y minus y z sub y equaling 2xy plus z. Factor out z sub y, you will have a 2xy plus z divided by, if you factor z sub y out of each of those, you will have a 1 again, minus 2xz minus y. And of course the second derivative has another notation, something to be careful with of how you play this. If I am taking the derivative with respect to x and then another derivative with respect to x, I do this first. So if I'm looking at f sub xy written this way, you take this derivative first, this second. And here you would do this first, then this second. The notation with the derivative, the actual notation, it goes backwards. This is how it's really written in the definition. This is what you do second. Mainly we're going to be using this, but you should be familiar with those. So find all second partial derivatives. There are plenty of those, such as, first I need to find f sub x, the derivative with respect to x, 1 times the sine of 2x minus 3y times 2. So f sub x is twice the sine of 2x minus 3y. I need the first derivative to get to the second. And f sub y. Actually, let me finish all of the f sub x's. So here now I have 2 of those to do. I need to take the derivative of this with respect to x. That should have been the product rule, no? Plus x times the cosine of 2. Okay, I messed up. You guys should say something. F sub x product rule. Derivative of the first times the second plus the first derivative of the second is the cosine of 2x minus 3y times 2. I got confused a bit there. I apologize. And of course the fun is not taking the derivative only. The fun is undoing this. Finding the antiderivative. That's where the real fun is. So now I have the first derivative. You need the first derivative to take the second. So in the second I have two of them. One, I'm going to take a derivative of this with respect to x. That's the cosine of 2x minus 3y times 2. Plus the product rule. Derivative of the first times the second. Plus the first times derivative of sine negative the sine of 2x minus 3y times another 2. So f sub xx is this mess. Let me write it out. 2 of those plus 2 of those is 4 of those. Plus 4x, messed up again, it's really minus 4x the sine of 2x minus 3y. That's one of them. I'm going to go to this derivative again and take the derivative of x with respect to y. It says all of them, right? So with respect to y, this is the cosine of 2x minus 3y times a negative 3. Plus, as far as y is concerned, that's a constant. You ignore that. Derivative of sine is negative the sine of 2x minus 3y times a negative 3. If I clean that up a bit, I would say f sub xy is negative 3 the cosine of 2x minus 3y minus 6x plus negative times a negative 6x the sine of 2x minus 3y. That's half of the problem. What's the other half? The other half is I'm going to find f sub y. F sub y first, that is, x is a constant, the cosine of 2x minus 3y times a negative 3. So, f sub y is going to be negative 3x, the cosine of 2x minus 3y. Now I need to take two derivatives of that. First derivative is going to be in terms of f sub y, y. That would be, that's a constant, derivative of cosine is negative the sine times a negative 3. So f sub y, y is done. That is negative 3 negatives, that's a negative 9x the sine of 2x minus 3y. That takes care of this. And to find f sub yx, I need to take a derivative of this with respect to x, the product rule. Derivative of the first times the second plus the first times derivative of cosine is the sine of 2x minus 3y times the derivative of the argument, which is a negative 3. So f sub yx would be, what would that be? That would be negative 3 the cosine of 2x minus 3y plus, something is not right. What did I mess up on? Wow. That would be a 9x times the sine of 2x minus 3y. There's a mistake. Let me find it really quick. I found it. It's right there. Let's go over that right there. If I take the derivative of this with respect to x, so we said derivative of negative 3x is negative 3 times the cosine, that works, plus minus 3x. Derivative of this with respect to x is negative the sine of 2xy minus 3y times the derivative with respect to x. With respect to x, it's a 2. So when you multiply those two, you get, and this should be negative, no, it should be positive. And this right here should be 6x. Okay, and you notice that those are negative. Derivative of cosine is negative the sine. So negative times a negative is a positive. Okay, now we're